Uh, Welcome everyone to the week 6 of this interactive session. And I hope you are enjoying the course and the lecture videos and the assignments as well. And thank you for posting your doubts in the discussion forum. And I hope they are clarified uh, to to the best uh, the the management can in clarifying the doubts. Okay. Uh, Okay, so if you remember in the last class, I mean in the last week, we looked into a class of flows transient, which were basically transient flows, and we looked into a problem which involved a pressure gradient, which was oscillating with time, and we were interested in calculating the resultant velocity field. Of course, the flow was unidirectional. If you remember, it was a pipe in which the pressure gradient was oscillating with time and with some amplitude g naught and frequency omega. And we were interested in finding out the resultant flow field, which will also oscillate with time as a result of the applied pressure gradient. So we saw that because of these fact that the velocity field now is a function of time in addition to it being a function of space, the governing equations where so the Navier-Stokes equations where PDE is in nature, that means they are partial differential equation, and we looked into the fact that we want to seek time periodic solution, because of which we considered that the velocity field, which essentially was a function of z and t, we wrote it as some real part of some u hat of some r times, if you remember, it was some e power that that time that we wrote. So basically, it was some real part of u hat of r times e power it. That's something that we wrote. It's something like that. So the idea was that since the governing equations were linear, and we said that the fluid will also move in phase with the applied pressure gradients, renders us the fact that we could now use that form of the solution. Typically, once again, because of the fact that the governing equations are linear, and we were looking for time periodic solutions as a part of our analysis. So by time periodic solutions, I want to clarify that we are neglecting the initial transients, and we are saying that, okay, now we are looking at a time when the fluid will also have a pure oscillatory motion, just like the applied pressure gradient. And that's the reason why we consider the solution as some. So if you remember, we looked into the solutions, the form of the solution as something like this. So that's what I was saying. We consider it as some real part of u hat of r times e power I t bar, and we non-dimensionalize the equations. That's the part that we did. And in doing so, what we did is our PDE, which was our original Navier-Stokes equation in the z direction, which was a function of r and t, that's simplified into an ODE of this form. And then what we saw is we took a transformation of this variable r bar. Of course, we said that this ODE is non-homogeneous, so it has two solutions, the particular integral and the complementary function. And we said that by inspection, the particular integral just came out to be 1 by I alpha squared. That was simple because the right-hand side of this equation was just a constant. And then we said that the complementary function eventually gave rise to the modified Bessel's function because of the nature of the ODE we had. And then we said that the solutions were nothing but the linear combination of the two Bessel's function of the two kinds. And then we argued that since my problem was bounded, the second Bessel function, that is the Bessel function, the modified Bessel function of the second kind, they basically goes so the coefficient, since the modified Bessel function of the second kind blows up at the singular point when r bar is equal to 0, or r tilde is equal to 0 in this case. So we said that the coefficient for the flow to be bounded, the coefficient has to be equals to 0. And from that we evaluated the coefficient b1. And from the other boundary condition, that is the no slip boundary condition at the walls, we said that we evaluated the constant a1. So this is something that we did. And then we said that the entire velocity field is just going to be the real part of this term times e power it. So that's the velocity field that we got as a part of our solution. So this was one class of important flows and an important problem that we solved in the last class. So today we will increase so what we will do is, today instead of looking into 1D problems, we will now look into 2D problems. A simpler problem of this we already did. That if you remember, there was two cylinders that are rotating with individual angular velocities omega 1 and omega 2, and there was an applied pressure gradient. That problem was relatively simple, but in this problem we'll kind of deal with a more generalized solution to this problem, And I call this problem as a flow past the rotating porous cylinder, which essentially is a 2D problem now because of because of the fact that the cylinders are rotating, and of course it's also a porous. It's a porous cylinder, means that there will be a suction inside the surface of the cylinder. There will be kind of a radial suction that will take place. So this is something that we will solve it in this week. I mean in this class, and just for you to have a physical look at or just for you to have a look at the physical problem, this is what the paradigm looks like. So as I said, there is a cylinder which is rotating with angular velocity in the counterclockwise sense with some magnitude omega, and this cylinder is essentially porous, meaning that there is now, so when the cylinder, as and when the cylinder rotates, there is also a radial suction of the fluid that takes place through the cylinder walls because of the fact that the cylinder is now porous, which means the earlier no penetration boundary condition that we used will get modified. It will kind of get modified slightly because of the fact that there is a radial suction here. And as a result of which, I think you could appreciate that the flow field is essentially going to be 2D. One, because of the fact that the cylinder is rotating with some omega, because of which we will see a u theta component of velocity. And then since there is a radial suction, so the fluid will also move inward as and when the cylinder basically rotates in the theta direction, meaning that there will also be an ur component of velocity because of the fact that there is a radial suction. Okay, and the other underlying assumptions are that we consider the length of the cylinder to be infinitely large in the z direction, that is along the axial length, meaning that all the variables will be independent of z. It's kind of same as the fully developed solution that we saw. And also it's an axisymmetric problem that I think you could appreciate because there is nothing which is varying along the theta direction because of the fact that your cylinder is rotating with a constant angular velocity. So we will use two of the important assumptions in simplifying this analysis. The first is that variables are, so first is a consequence of the fact that the cylinder is infinitely large, meaning that my variables are independent independent of z. Okay, and theta, this is because of the fact that my problem is axisymmetric, and this is because of the fact that this is kind of like the fully developed condition. Okay, all right. So this means that the non-zero velocities which we seek to find out in this problem, that is the urs and u thetas, these are simply going to be a function of r only. Although this is a 2D problem. So this is one simplification that we can do by considering the underlying assumptions that I just now stated. Okay. So this is the physical picture of the problem, and having said that, this is something that I already said, that the cylinders are rotating with some omega. Okay, it extends to infinity, the length extends to infinity in the plus z direction. Okay, it's an axisymmetric problem, and since the length extends to infinity, we can safely assume that uz is equal to 0, and then we have only two non-zero components of velocity, ur and uz and u theta, sorry, which are just a function of r only. Okay, and also one important assumption that we'll consider is that, see, the cylinders are rotating due to which there is a disturbance in the flow around the vicinity of the cylinder, and this disturbance, it's kind of like we can imagine that this disturbance will go to 0 as we move far away from the cylinder, because there is no kind of a background flow that is affecting the flow field at near the vicinity of the cylinder. In fact, it's the rotation of the cylinder itself which is actually disturbing the flow field and the radial suction also, and these two mechanisms are solely responsible for disturbing the flow field near the vicinity of the cylinder, but there is nothing which disturbs the bulk fluid at a distance where we move far away from the cylinder, meaning that all the velocity components, that is ur and u theta, they will go to oblivion when r tends to infinity. Okay. So this is the physical picture of the problem. I will stop here for a couple of minutes just for you to digest the problem and to understand what the physical picture essentially looks like. Typically, because it's a 2D problem that we'll be dealing with, and you need to understand that why there is a non-zero ur component of velocity in addition to the expected non-zero u theta component of velocity, and that is typically due to the fact that we have a radial suction because of the nature of the surface of the cylinder, which is porous, which you can imagine that it's a porous cylinder, kind of a sponge like thing. Okay. All right. I hope this is clear. So having said that, then the objectives of this exercise are as follows. The first task is to write down all the boundary conditions of the problem. This is similar to one of the assignment problems that you have. So we will start off with this. So we'll write all the boundary conditions. Then once we state all the boundary conditions pertinent to all the variables of interest, then we will write down the governing equations. But as I said, we will be dealing non-dimensionally. This is again because of the fact that non-dimensional, as we saw it in the last class, that you see there's tremendous power when we write down equations or solutions non-dimensionally, because the variables of it, then the parameters or the variables kind of so the variables become order 1 quantities. That is one thing that you can argue. And the parameters become universal. For instance, in the last problem, we saw that there was a parameter that pop out, which was the frequency dependent Reynolds number, which is alpha square. Now the frequency dependent Reynolds number, it is not just meant for one fluid. It's a universal parameter, okay, which can be tuned as per the fluid that we are dealing with. But that parameter in general is a universal parameter. So that is the power and the beauty of non-dimensionalization, and that's why we will also be treating we'll also be doing this problem. We'll be starting off this problem. We'll be writing the governing equation non-dimensionally. And luckily or unluckily for us, this time what they said is that they have stated that use these characteristic scales in order to non-dimensionalize the problem. For instance, if you remember in the last problem, we did not encounter the choice of scales because we had the natural scales that we had. For instance, the pressure gradient was so the applied pressure gradient, which was oscillating in time, gave us the inherent time scale, and we had the inherent length scale. And from the velocity profile, from the Navier-Stokes equation, we evaluated what would be the scale for the velocity would be. But here in this problem, what they said is that they asked us specifically to calculate, to non-dimensionalize the equation using a certain scales that they have already given us a priori. For instance, the characteristic radial velocity, they have said this as the suction velocity, which is u, because I stated that there is a radial suction which is equal to minus u on the surface, and they say that okay, now in your non-dimensional equations you need to non-dimensionalize the r velocity using the characteristic velocity, which is nothing but the radial suction, which is u. Okay. And they stated that for the theta component of velocity, you cannot use the same characteristic velocity, rather use the velocity on the surface of the cylinder, which is nothing but omega a, the tangential velocity on the surface of the cylinder, as your characteristic velocity in the theta direction. So these are the scales that they have given us a priori, and they asked us to basically calculate this. So the point of giving these scales is that, see, now there are two velocity field instead of one velocity field which we encountered in the previous problem, meaning that it may so happen that sometimes the cylinders will rotate so fast and the radial suction will be so low. That means if we just use a single characteristic variable, this may not be this may not help us to basically capture the physics of the problem. That's the prime point of interest, and that's the reason why, since there are actually two mechanisms which is governing the flow field, it is more safe and it is more customary to define two scales which indicate the strength of one mechanism with respect to the other. And that's the reason why they have given us two separate scales for two separate velocity fields in this problem. Okay. And and that is the reason why they gave us a different scale for the radial component of velocity and a different scale for the theta component of velocity. And I hope you realize why these two different scales are there. So which means you can also, like, if you just pay a closer look, you can basically think that there will be some parameter in the governing equation which will dictate how strong the radial suction and the angular motion of the cylinder is. And we will see very shortly that indeed there is a parameter which is of course a non-dimensional parameter, but it will dictate how strong the radial suction of the flow is with respect to the angular velocities of the cylinder on its surface. Okay, meaning that there will be a parameter which will dictate the ratio of u by omega a. And we will see shortly that indeed if you do the correct non-dimensionalization, you will indeed get up a parameter which will be of this form, and we will see that very shortly. Okay, so that is the idea of giving two scales for the velocity. Now for the pressure, they say that the pressure scales as the advection term, and that's why they have also said that the scale for pressure is rho times u square, and the u, the choice of the characteristic velocity for pressure, for scaling pressure, they have considered it as u theta c, which is the characteristic velocity in the theta direction, which is omega a. Meaning that my scale for pressure that they have already given is nothing but rho times omega square a square. that is just the advection scale for pressure that they have given us. Okay, and the length scale, that's a trivial case, because we just have a single length scale in this problem. So the length scale is nothing but the radius of the cylinder, which is just a. Okay, so so these are the scales that they have given to us, and using these scales, we basically need to derive the non-dimensional governing equations, and that is something that we'll do. And once we derive the non-dimensional governing equations and the non-dimensional boundary conditions, of course, the next trivial task is to basically solve for the flow fields, which is just ur and u theta. Of course, they are going to be just a function of time. And now, once we are done with solving the flow fields, they have also asked us a more important thing, that they also asked us to evaluate the pressure field, saying that my pressure goes to some constant P naught at far field from the vicinity near the cylinder. I mean, near the vicinity of the cylinder. So it says that far away from the cylinder, my pressure is just P naught. That is something that they have stated. Okay, so these are the tasks that we will do, and we will start off these tasks very systematically, one by one. Okay, so I hope it is clear what are the objectives that needs to be done. So we will start off by the first task, which is nothing but the boundary conditions, because the first task is to write down the boundary conditions, and we will start off with that. Okay, all right. So boundary conditions, these are rather simple, because we know that we just have two components of velocity, ur and u theta. We know that at r equal to at r basically equals to a, my ur is just going to be minus u. That's the inward suction that is taking place on the surface of the porous cylinder. Okay, so so the boundary condition is ur is that ur at r equals to a. This is basically equal to minus u. Okay, and they have already stated that my velocities, all the velocities will basically go to oblivion when we move far away from the cylinder, meaning that my ur, when r tending to infinity, this is equals to 0. Okay, all right. So these two are the boundary conditions for ur. Let's also write down the boundary conditions for u theta. So that's also simple. U theta at r equal to a, we already saw that this just boils down to omega times a. So we saw that vectorically also we saw that this indeed becomes omega times a, because omega has a direction in the ez direction and a has a direction in the er direction. So actually it's the cross product of ez cross er which gives us e theta, and this e theta is indeed in the direction of u theta, because u theta essentially acts in the e theta direction, and that's why the magnitude just becomes omega times a. I hope you can recollect this when we did the same sort of analysis when we solved for the Taylor-Kuet flow, that is the two rotating cylinders that are rotating coaxially. Okay, so that's the boundary conditions for u theta on the surface of the cylinder. And then I said that u theta as r tending to infinity, that basically goes to 0, again because of the fact that the disturbances will die down when we move far away from the cylinder. Okay, so these are the boundary conditions for the velocities. We also have one more boundary condition, that is for pressure, that pressure when my pressure when r tends to infinity is just some p naught. Okay, that's it. So these are the boundary conditions that they asked us to find out in the first task, and we did it. So I hope you realize that there are primarily three unknowns that we are trying to solve for: my ur, u theta, and pressure. So these are the essential unknowns that we will be solving for. And also we have three equations. Why? Because we have the r momentum equation, we have the theta momentum equation, and also we have the continuity equation, which means we are dealing with a closed system. So we have three unknowns, and then we have three equations. Okay, so that's it. So it's kind of a closed system. Okay, it's a closed system. That means, yes, indeed, we can find some sort of, what to say, some sort of unique solutions to this analysis. But there is a very important thing that we'll see in this problem towards the end, is that even though this is a closed system, that is three unknowns and three equations, there is only a range of a parameter, which we will see that parameter indeed comes out to be Reynolds number, and we will see that only for a certain range of Reynolds number we can analytically derive closed form solutions to this problem. And that is actually because of the that is actually because of the nature of the boundary conditions that we have in this problem. Okay, so we will see that shortly, that So we'll do all the analysis and then we will argue it in the end that only in a particular range of Reynolds number we can derive closed form analytical solutions to this problem. Although the number of unknowns are 3 and the number of equations are also 3. And we will see that so as to why this is the case, okay? And yeah, so that's the idea basically that I want to convey. All right, so I hope this is clear. That's the first task. So we wrote down the boundary conditions. So next, then so what was the next task? The next task is to derive, govern the non-dimensional governing equations. And we know that for deriving non-dimensional governing equations, as we saw it in the last class, we need to start off with the characteristic variables. And luckily, we have all the characteristic variables that so the characteristic variables they have already provided us in this problem. Okay. So we'll start off with this. So we'll start off by defining the non-dimensional parameters, just how we did it in the last class, that we will define non-dimensional variables. So task 2 is to evaluate non-dimensional governing equations. Okay, so all right, so let's do it. So in order to derive non-dimensional equations, as I said, first we need to non-dimensionalize our dimensional variables. So let's do that. So we know that URC, which is the characteristic velocity of the R component of velocity, that is nothing but U, that is the magnitude of the radial suction. This means if I now define a non-dimensional UR, which says so the UR bar is basically the non-dimensional version of the radial component of velocity. This will be nothing but the dimensional UR divided by URC, that is the characteristic radial velocity, which is nothing but UR by U. Okay. Similarly, we know that my U theta C, the characteristic velocity in the theta direction, is omega A, which means that my non-dimensional theta, that is U theta bar, is just going to be my dimensional theta divided by U divided by the characteristic theta, and then this simply comes out to be U theta by omega times A. Okay. Then I can write that my non-dimensional R bar, which is the non-dimensional radial length, is just going to be the dimensional radial length divided by my characteristic scale, which is just going to be A, because RC, which is the characteristic length scale, is nothing but the radius of the cylinder. Okay. And similarly, there is also pressure. So pressure, I can write it as P by PC. And this is also given to us because it just turns, because PC that they have stated, so they have also given that the PC, the characteristic pressure, is just rho times omega square A square. Okay, or it is rho times U theta C square, basically, which is nothing but omega, omega A. So this PC basically turns out to be rho times omega square A square, and you can appreciate that this is indeed the advection scale for pressure. Okay, so that's it. So these are the non-dimensional variables that we derive. So these are UR bar, okay, U theta bar, P bar, R bar. Basically, these are all the variables that we would require in solving the R and the theta momentum equations. Okay. All right. I hope this is clear. I will again stop here for a couple of minutes, and and I hope you are clear on this. Okay. All right. So once this is done, now let's just go ahead and derive the non-dimensional equation. So what do we need to do? We'll start off from the dimensional form of the R and theta momentum equation, and then substitute the non-dimensional variables in the dimensional equations to basically get the non-dimensional equations. That's the idea behind behind getting the non-dimensionalized version of the dimensional equations. Okay. So if that is the case, we'll start off by the R momentum equation. So the R momentum equation will look like what? So we'll invoke the assumptions. We'll not start from the big R momentum equation. I mean, you guys, so we have done this multiple times. So I'll start off by implementing the assumptions, and then I'll just write down the simplified form by writing all the assumptions that we stated a priori. Okay. So R momentum equations, I'll write it as simplified. So it just turns out to be something like this. So it becomes rho times UR del UR by del R, okay, minus rho U theta squared by R, okay, and then this becomes mu times 1 upon r del r of r times del ur by del r. Okay, I hope this is clear. And then I have one more term which is ur by r squared, and then I have minus of del p by del r, which is nothing but the pressure gradient. Okay, all right. So this, I hope you realize that this is the dimensional form of the r of the simplified r momentum equation by invoking all the assumptions. For instance, steady flow, and then that the variables are independent of z. They are axisymmetric, meaning that they are independent of theta. We'll just have two components of velocity, which is ur and u theta, only varying along the r direction. Okay, so this is basically the simplified r momentum equations written in a dimensional form. So I hope you realize that now what we'll do is we will typically non-dimensionalize the equation by using the characteristic variable that that we that we wrote here. Okay, so let's do this. So then what does first term become? So the first term becomes rho times u square, and I hope you are aware of how this non-dimensionalization is done, because we did this multiple times in the in the last meeting as well. So it is rho u square by a times ur bar del ur bar by del r bar. Okay, and then this becomes minus of what? So rho is going to be there. So this u comes because of the fact that my urc is equal to u. So that's why there is a urc square, which is just u square, and that's why we have a capital U square here. And similarly from here I would get basically rho times u theta c squared by a, and u theta c squared will just give me omega squared times a squared. So that's why we'll have what? Rho times omega squared a squared by a. Okay, and then I have just this u theta bar squared by r bar to be precise. Okay, all right, and then let's look at the viscous term. So the viscous term will give me what? So the viscous term will give me mu u by a squared. That is again because of the fact that I will get a u coming out from this ur, and then this r and this r will get cancelled. So from these two, I'll get a squared that will come out basically, and that's why we have mu u by a squared. And this term will also give us the same, this term will also spit out the same term, which is just u by a squared. So that's why I'll take the u by a squared common from these two terms, and then club them with mu basically. So that's the thing that we did. I hope it is clear. It's just non-dimensionalization that we are doing. That's it. So it's 1 by r del r of r times del ur by del r. Okay. And then I have what? And of course, these are going to be bar terms now because they are all non-dimensional. Okay. And this is minus ur bar by r bar squared. Okay. And then from the pressure also, I'll have Pc by A, because del P by del R will just give me, Pc by A times del P bar by del R bar. And Pc I know is rho times omega squared A squared. This is already given to us in the problem. Okay. So Pc is just going to be rho times omega squared times A squared, and I have a A below. And then this term will just become del P bar by del R bar. Okay. I think so far so good. And all right, so now what we'll do is we'll do one thing. We'll multiply this entire equation by a squared by mu a. Okay, that's what we'll do. So just to simplify, what we'll do is we'll multiply by a square by mu times u. Okay, that is just the reciprocal of this term. And let's see what do we get. So from these terms, what we'll get is we'll get something like this. We'll get rho, sorry, yeah, so we'll get what? We'll get rho u squared by a times a squared by mu u, that is from the first term, and then I have this term u bar del u bar by del r bar, okay? And then I have this term, so I have minus of rho omega squared a squared by a times a squared by mu u, okay? U theta squared, u bar theta squared by r bar, okay? And then this term would just give me 1 because I have multiplied with the reciprocal, so I will just have what? I'll just have 1 upon r bar del r bar of r bar times del u r bar by del r bar, okay? And I'm just going to have one more term which is minus u r bar by r bar squared, okay? This is the viscous term. And of course I also have the pressure, so pressure is just going to be rho times what? Rho times omega squared a squared by a multiplied by a squared by mu u, okay, times there is this term which is just going to be del p bar by del r bar, okay, or I'll just write this term below just for clarity, times del p bar by del r bar. Okay, all right. So what we did is we just multiplied the entire equation by a square by mu a just to see how different, non-dimensional parameters pop up in this analysis. So what I can do is I can cancel this. I can cancel this. So from this, I have just, so what do we have? I have rho ua by mu, basically. Okay, that is something that we get from here. And from here, let's see what we get. So if I simplify this, then this a and this a cancels, okay, and I have what? I have, okay, so I have mu times u. All right, so what can we write about this term? Okay, so let's simplify this term and let's see what do we get. So I have rho omega squared a squared, okay, rather I think it's okay, rho omega squared a squared times I get a by mu u. So what I will do is I will multiply this I'll multiply this above and below this term. I mean, I'll just multiply this with u basically. So what I'll do is I'll put a u here and I'll put another u here. And if I do that, I can just say that it is rho times au, okay, divided by mu times what? Times omega a by u whole squared. Okay, something like this. I hope you are with me on this so far. Okay, so what I did is, if I just simplify, I just end up getting this. And what I do is I'll multiply and divide, by u. And this doesn't change anything, which means this term can be simplified into rho au by mu times omega a by u whole squared. Okay, and we will see why I have done this basically. And the similar thing can also be done for this term, because this term, as you can see, this term and this term is just identical, which means this term will also simplify to basically this. Okay, and let's just write it down, all the simplified form. So what I have is, I have in the first term I have rho ua by mu, okay, times ur bar del ur bar by del r bar, okay. The second term I have something like this, it is rho ua by mu times omega a by u whole squared, okay. And then I have this term which is u theta squared, or these are bar quantities, I forgot to write. This is u theta bar squared by r bar, okay. And then on the right hand side I have this term which is unchanged, 1 by r bar del r bar of r bar times, what, del u r bar by del r bar, okay, minus u r bar by r bar squared, okay. And then the same term basically, that is just this, okay, with the pressure gradient. So I have what? I have just minus rho u a by mu times omega A by U whole squared times del P bar by del R bar. All right. So that's the simplified. So that's all the simplifications that we did in the in the theta moment in the R momentum equation. Sorry, and uh, and that's we get. So now and that is what we get. So now if we have a closed loop, what is this? This is rho velocity, the length scale multiplied by mu, and the velocity is nothing but the suction velocity. So it is this kind of like the suction Reynolds number. We'll call it as Re. We'll call this term as Re, which is nothing but the suction Reynolds number. Okay. And then what is this term? It is, if you now have a close look as this term, it is what? It is suction Reynolds number multiplied by the characteristic velocity, the characteristic, theta direction velocity to the characteristic, r direction velocity, which which is kind of an which dictates a parameter. So as to so what is this? So first of all, you need to realize that this is a non-dimensional parameter, because we have a velocity here, we also have a velocity here. And what does this parameter say? This parameter says that, okay, it portrays the strength of the rotational velocity of the cylinder with respect to the inlet suction velocity. Or in other words, this parameter says that how strong is the rotation of the cylinder with respect to the inlet, with respect to the injection of the fluid taking place through the surface of the cylinder. For instance, if I say, and of course, so then I can write this term, this UA by the omega A by U term, that this term, I'll write it as some U tilde. Okay. So this term is nothing but then U tilde squared basically. And what does U tilde say? Where this U tilde is nothing but omega A by U. I'll write it down here, that this U tilde is nothing but omega A by U. And what does this portray? It portrays the strength of the rotational velocities to the to the inward suction. Okay. So this U tilde is nothing but U theta C, the characteristic rotational velocity, to the characteristic suction velocity, to the characteristic radial velocity, which is nothing but a suction velocity. And it portrays the strength of the two velocity scales, something like this, of the two velocity scales. Okay. It is just that if I now say, so you can appreciate that if I now say that the cylinders are rotating very much faster, then with respect to, if I now say that the cylinders are rotating very much faster with respect to, the suction, then I will say that this U tilde is very much larger than 1 with respect to this Reynolds number, meaning that this term will now dominate over the other terms. Okay. So this now give us a sense of the strength of how much one mechanism dominates over the other. On the other way around, if I say that the suction is stronger with respect to the rotation of the cylinder, then I will say that, okay, this term will become very less, which means that the other term will dominate more with respect to to basically this term. So you can appreciate and you can see how powerful is non-dimensionalization here. So it just says, just by tuning a single parameter, I can say which term dominates over the other. And this domination can be established because these terms, this U theta bar by R and UR, all these non-dimensional terms, these are order 1, which means that the magnitudes are dictated and reflected by this Reynolds number and U tilde. Okay, and I hope you can now realize that how much powerful indeed, how much powerful non-dimensionalization is. Okay. All right. So then I can just write these terms as what? I can write these terms as Reynolds number, okay, which is the suction Reynolds number multiplied by UR bar, okay, and then I have what? Del UR bar by del R bar, okay, and then I have what? I have the suction Reynolds number multiplied by U tilde, which gives us the scales, which gives us the ratio of the strengths that we just now discussed, and then I have what? I have this U theta bar squared by R bar, okay, and then the viscous term is just unaltered, so we don't have to really bother about this much. So it is 1 by R bar, okay, del R bar of r bar times del u r bar by del r bar. Okay, that's the viscous term, and then I have minus u r bar by r bar squared. Okay, and then again I have this term which is minus the suction Reynolds number times u tilde, and this is u tilde squared because I have this omega a by u. So I have this suction Reynolds number times u tilde squared times the pressure gradient, which is del p bar by del r bar. Okay, so that's it. That's the non-dimensionalized R momentum equations that we are asked to derive. So you can now see that so you can see this equation offers, you know, it offers many insights. First of all, I'll write it down. So this is the non-dimensionalized R momentum equation. Okay. Now this equation essentially, you know, offers us it offers us many insights. How? So I can write this equation. So what I will do is I'll divide these equations by, you know, by the Reynolds number basically. So then what do we get? What we get is, yeah, so you can do that, or okay, let's do it and see. So if I divide this entire equation by the Reynolds number, then what do we get? I get u r bar times del u r bar by del r bar, okay, minus u tilde squared times u theta bar squared by r bar, okay, and then what do we have? Just hold on, did I write any mistake? Okay, I think I'm correct. All right, anyways, so okay, so this is this term, and then so I'm dividing it by Reynolds number, so it is 1 upon Reynolds number, okay, and then this is 1 by r bar times del r bar of r bar times, you know, it becomes del u r bar by r bar, okay, and then I have minus u r bar by r bar squared, okay, and then I have u tilde times u tilde squared times del p bar by del r bar, okay. All right, so here is something that you can now realize. So we have done our part, that we have derived the non-dimensionalized, you know, R momentum equations in terms of the non-dimensional variable, that is the suction Reynolds number and u tilde, okay. But you can now understand that, let's say now I consider a scenario when my Reynolds number basically goes to 0. That is, so this limit of Reynolds number going to 0 is known as the creeping flows, okay. So you can now understand, and I consider, let's say, u tilde is order 1 basically. Okay, that means that the strength of omega and the strength of u are just the same. In that context, you can now understand that if my Reynolds number basically goes to 0, then 1 upon Reynolds number will basically go to infinity. That is something that you can realize, which means that the order of that this term, that is the viscous term, will solely dominate over the other terms, because this term will basically go to infinity because Reynolds number goes to 0, meaning that the order of magnitude of this term will be very much higher than the order of magnitude of all these three terms. Meaning that I will, in the limit when Reynolds number going to infinity, I can just write, so this equation just boils down to just this term becoming equals to 0. That is, the viscous term is just 0. And this is something you can appreciate because of the fact, that, you know, we did a correct set of non-dimensionalization in this analysis. So this is again one of the, you know, usefulness of, you know, writing equations non-dimensionally, okay. But anyway, that is something that we are not asked to find out. We are just asked to find out the non-dimensional R momentum equation, and this is something, you know, that we get. This or this is something that we basically get, okay. All right, I hope you are clear and with me so far. So we have derived the non-dimensional R momentum equations. Okay. So the next task, so we need to derive two non-dimensional equations. So the next task is basically to derive the theta momentum equation, and that we will see shortly, that the theta momentum equation. Okay. Now the theta momentum equations will again start off from the non-dimensional. We'll just do the similar analysis, but this time I'll just do it a little fast because we are just repeating things. I mean, again and again. Okay. So we'll start off from the simplified form. Okay, and a simplified form for the theta momentum equation is what? It is just rho times ur del u theta by del r plus u theta ur by r. Okay, and then this term becomes mu times 1 by r del r of r times del u theta by del r. Okay, and then I have minus of u theta by r squared. Will not have the pressure gradient term because of the fact that if I write the pressure gradient, it will just be del p by del theta, which will just go to 0 because of the fact that my problem is axisymmetric. Okay, I hope you can understand that. And then the task is just the same. We will just insert the non-dimensional variables, and I'll skip the intermediate steps because it's just the same thing. What you need to do is just write this ur as, so from here you will just get u times omega a by a as the, and there will be a row of course as basically the non the characteristic variable splitting out, and then we'll just have ur bar times del u theta bar by del r. That's the same thing that we have been doing repeatedly, so I'll just not write the intermediate steps. So I'll just write the form of the non-dimensional equation that we do after doing these analyses. Okay, so what we'll get is, we'll just get, you know, ur bar. You can do it at your end and just verify this. You'll just get the same thing. It's just the repetition of what we had been doing for the r momentum equation. So what we'll get is ur bar del u theta by del r bar plus u theta bar ur bar by r bar. Okay, and then you have 1 upon Reynolds number in this case, and then we'll just have 1 by r bar times del r bar of r bar times del u theta by r bar. Okay, and then I have minus of u theta by r bar squared. So that's it. That's the non-dimensional, theta momentum equation. I didn't do the intermediate steps because these are just the repetition of the things that we have been doing from the past 2 or 3 examples. So I have just skipped the steps, but I'll encourage you to do it at your end and verify it out, and indeed, get the idea that this is indeed true. So that's it. That is your, the non-dimensional theta momentum equation, of course. So I'll write it down. So this is your non-dimensional theta momentum equation. All right. I'll stop here for some time. I'll let you guys, try to understand what we did so far. I'll be back in 1 or 2 minutes. But in the meantime, you can try this non-dimensional out but at your end, and I'll be just back in 1 or 2 minutes. All right. Sorry for the interruption. So what we did is, so just let's do a quick recap of what we did, just that we have the continuity, because we just had a lot of math here. So we started off by, writing, by understanding the problem first, writing the boundary conditions, okay? In terms of the dimensional variables, of course, we can also write this in terms in non-dimensionally. And then what we did is we use the characteristic scales defined in our problem to basically, define our non-dimensional parameters, or sorry, the non-dimensional variables, uh, and then use these non-dimensional variables to basically non-dimensionalize the dimensional equations, for instance the R momentum equation. And then we saw that the non-dimensional R momentum equations can be written in terms of the non-dimensional variables and some parameters which, readily popped out of the analysis because of the choice of scales that we are using in this problem. For instance, we get a Reynolds number which we call it as the suction Reynolds number, and we get a parameter u tilde which dictates how strong my rotation of the cylinder is with respect to the suction velocity. Okay, and this is what u tilde portrays. And then we get basically this this R momentum equation, okay, uh, non-dimensionally. And then what we see is, if we now see the theta momentum equation, I skip the steps, but this is how, the non-dimensional form of the theta momentum equation would essentially, look like. All right. So we are not done yet, right? Because we still need to find out the solution for ur bar and u theta bar. Okay, but this is where we encounter a problem. See, the problem is we cannot directly solve this equation for u theta because ur is unknown. Okay, that is number one problem. The second problem is, okay, then you will say that, okay, let's see the R momentum equation. Okay, if we now see the R momentum equation, we cannot directly solve for ur because u theta is not known. Also, p bar is u theta bar is also not known. Also, the pressure is not known. Okay, the pressure is also something that we need to evaluate as a part of our solution. So it's like we have two equations, but they are kind of coupled to one another. Okay, so this means that it's a PDE and it's a coupled set of PDE that we are currently looking at. So then what can we do is something that we'll try to understand. Okay, so the way out is that we have not used one more equation, which is nothing but the continuity equation. So let's see what the continuity equation gives us, and let's see if we have a way out by using the continuity equation. So if I see the continuity equation, so if we see the continuity equation, that's it's see the continuity equation will have u theta and, this so the continuity equation will have derivative of u theta with respect to theta, that will just go out to be equal to 0 because it's an axisymmetric flow, and uz is indeed 0. So the simplified form of the continuity equation, I hope you can understand what I'm trying to say, is basically nothing but del r of r times ur. And then he'll ask me, why did I not write the u theta term? Because of the fact that the u theta term would be something like this, del theta of u theta, and I think there will be one r here. But we know that del theta of u theta is equal to 0. Okay? Because of the fact that my problem is axisymmetric. And that's why we'll not have u theta. And uz is anyway 0. Uh, that is because of the fact that, my cylinder is infinitely long in the z direction. And we don't have any mechanism to actuate the flow in the z direction, to be precise. Okay, so this is what the continuity equation just boils down to be. And then if I now non-dimensionalize my continuity equation, what we'll get? So we'll get it like, we'll just get u times del r bar of r bar ur bar to be equals to 0, which means that this term can't be equal to 0, because if this is 0, then we will end up getting a trivial solution, meaning that this can be, cancelled. This can be, I mean, since this is not, sorry, I told the other way around. So this can't be equals to 0 because there is a physical suction that is taking place, meaning that this should be then equal to 0 if we have the right hand side to be equal to 0, which means that del r bar of r bar times ur bar, this is equals to 0. Okay, and then if I simplify this term, what do you get? If I just use the product rule, I'll have ur bar plus r bar times del ur bar by del r bar, and this is equals to 0. And then, if I bring that other term to the other side, I'll just have r bar times del u r bar by r bar equal to minus u r bar. And so what I can now do is I can bring this del u r bar by minus of del u r bar by r bar on one end, and then I have what? I have del r bar by r bar. Okay, which means that just by using a variable separation, I think I can uniquely get u r bar. And let's just try and do this. So if I integrate this, okay, with respect to dr bar, of course, then what I'll get? I'll get ln of u r bar equal to minus ln of r bar plus a constant ln c. Okay, and then what I can do? I can write this as u r bar equal to ln of, this would be what? This would be c by r bar. Okay, and then I can just say that my u r bar is just c by r bar. That's it. That's my that's my u r bar. So luckily what we saw is just by using the continuity equation, we we were, and by invoking all the assumptions, we were so it was possible for us to uniquely determine what is ur bar would be. Okay, so that's the escape that we basically got. But it's not always that the continuity equation will give us the velocity profile, but in this case, and considering the following assumptions, it was possible for us to uniquely determine ur bar from the continuity equation. Okay, and in this way the continuity equation helps sometimes in our numericals. So let's now use the boundary conditions to basically get a profile for ur bar, because the c needs to be evaluated. So what we have is that at r equals to a, we have ur equal to minus u. So if I write it in non-dimensional form, I have at r bar equals to 1, I have ur bar to be equal to minus 1. And then if I just use it, then I'll get, therefore, so what I will get? I will get minus 1 equal to c by 1, which means my c just comes out to be equal to minus 1. So this means that the velocity profile for ur, that is ur bar in non-dimensional sense, is just minus 1 by r bar. That's it. That's my non-dimensional ur component of velocity. So luckily it just came out to be so simple that you just get the ur bar from the continuity equation, or like you get the r component of velocity from the continuity equation. But this is not always the case. Here we encountered this scenario. All right. Then I think some of the problems are solved, which we thought that it would not help us in getting the answer, because now I can simply use the theta momentum equation, because I know the fact that my ur bar is just minus 1 by r bar, to basically calculate my u theta. Okay, because one of the velocity components are known, we will use the theta momentum equations, because it doesn't have pressure. So the only unknown that we have in the theta momentum equation is u theta. And we will do this by substituting the form of ur bar, which is just minus 1 by r bar. Okay, so that's it. So what we'll do is, so I'll name these equations. I'll name this as equation 2. I will name this as equation 1, that is the r momentum. See, we cannot do this in the r momentum, because in r momentum we also have pressure, which is unknown. So it's like two unknowns, u theta and pressure, and just one known, which is ur bar. So that is not possible. So once we get u theta and ur, we will use r momentum to get the pressure. But before that, we will use the theta momentum to basically get u theta, and then from u theta and the fact that ur is known, we will use the r momentum to get the pressure. So that's the algorithm that we will basically follow. But for now, we will use, so what we'll do is we will substitute, substitute, okay, ur bar in equation 2, which is nothing but the theta momentum equation, to get u theta bar. And let's do this substitution. So let's see. So what do we have? So let's see the theta momentum. So one thing that we can do is that since this u theta is just a function of r, this partial derivatives can be written now in terms of complete derivative. That is one thing. The second thing, I know that this ur bar is just minus of 1 by r bar, so I'll substitute wherever there is ur bar, I'll substitute it as minus of 1 by r bar. I think there is only two places where we have ur bar. Here I'll substitute it as minus of 1 by r bar, and I'll also substitute it here. Okay, so that's it. Let's do this. So Reynolds number times minus of 1 by r bar, and the partial derivatives, I'll write it as now ordinary derivatives because of the fact that my u theta bar and also ur bar is just a function of r only. Okay, so this becomes du theta bar by dr bar minus u theta bar by r bar squared. Okay, and then I have this term 1 by r bar d r bar of r bar times d u theta bar by dr bar. Okay, and I have one more term which is minus of u theta bar by r bar squared. All right, so now this looks a kind of solvable because now this is an ODE and the only unknown is u theta, but it's kind of a nasty looking ODE. So we'll just do some simplification and let's see what this ODE is, what this ODE turn out to be. Okay, so if I do certain simplification, I can write, so I'll just write the first term. I'll write it as minus Reynolds number by r bar times d u theta bar by dr bar minus Reynolds number. Remember, this Reynolds number is the suction Reynolds number. Okay, and then this is u theta bar by r bar squared, and then I'll break down this thing by using the product rule. So if I do that, I'll just get what? I'll get d2 u theta bar by dr bar squared plus 1 upon r bar d u theta bar by dr bar. I think I'm on the right track. Okay, if you do this, if you apply the product rule here, you will basically get this only. And I hope I'm correct here. Okay, I mean the algebra is correct here. Minus u theta bar by r bar squared. Okay, so what I'll do is I'll club the terms having the same, the same order of the derivative, meaning that I'll club this term with this term, I'll club this term with this term. Okay, and if I do this clubbing, what I will get is the second derivative term would just be d2 u theta bar by dr bar squared plus the first derivative term will just give us 1 plus Reynolds number by r bar. Okay, then this is multiplied with du theta bar by dr bar. Okay, and the other term would just give me what? It will just give me Reynolds number minus 1 by r bar squared u theta bar. Okay, I hope I'm correct. All right, so far a little more simplified. Okay, we'll do one more step and then you will see a nice little thing that will come up. Okay, so what I'll do is I'll multiply by r bar squared both sides basically, and then what I will get is I'll get something like it. So this r bar squared d2 u theta by dr bar squared plus r bar 1 plus of Reynolds number, okay, times du theta bar by dr bar, okay, plus Reynolds number minus 1 times u theta bar, and this is equals to 0. Okay, so what is this? If you have a close look at this expression, at this equation, we saw a similar equation when we were solving the Taylor-Quate flow basically. And if you remember, these equations we called it as the Euler-Cauchy equation or equidimensional equation. Okay, because of the fact that the dimension of all these terms are just the same, and we argued that just by looking at, so we got a similar expression when we are solving the Taylor-Quate flow. So these kind of equations are known as Euler-Cauchy equation. I hope you can now recall. Okay, these are known as Euler-Cauchy equation, and sometimes they are also called as equidimensional equations. Okay, now since we got a known familiar equation which is the Euler-Cauchy equation, we know that what form of u theta will satisfy this equation. So we know that u theta bar will be just some form of r bar to the power k. Okay, because this is the way of solving the Euler-Cauchy equation. So we'll assume that u theta bar is of this form, basically r bar to the power k. And this form, if you recollect, we said that why this form is taken. This is so taken because the dimensions of these terms are just the same, which means that we'll just end up getting an algebraic equation of k basically, and we will see that. So if u theta is this, then what is this term? du theta bar by dr bar, it will just be k times r bar power k minus 1. And the other term, d2 u theta bar by dr bar squared, this term would be k times k minus 1 r bar power k minus 2. Okay. All right. So then we just need to substitute this. So if we substitute this into this equation, let's name this. Let's name this as what? Maybe I'll name it as equation. So this, I'll call it this 3. I'll name this as equation 4 maybe. So if I substitute this in 4, then what do we get? I'll just end up getting something like this. You can do this substitution. You will get what? From this term, you'll get k into k minus. So from here, we'll just get k into k minus 1. Because there is an r square and there is an r bar power k minus 2, we'll just end up getting an r power k. And this r power k will appear everywhere. It will appear here, it will appear here, and it will appear here. And then we can just basically take this common and we'll argue that r power k cannot be equal to 0. And then we'll just say that this term will simply come out to be equal to 0. It's just same thing that we did in the Taylor-Quitt flow. Okay. So I hope you can understand now that why are we doing this here. So it will just become k into k minus 1 plus r Reynolds, so re plus 1 times k plus re minus 1 equals to 0. That's very simple. Just substitute this here and then you take r power k common and then inside the bracket, so it will be r power k, and then a term inside the bracket is just going to be this. And then we'll argue that since r power k times the term inside the bracket is equal to 0, and since this cannot be equals to 0, meaning that this will basically be equals to 0, and that is something that we wrote here. Okay. So if this is the case, then let's solve this for k, because that's the thing that we want here. So it will just be k square plus re times k plus re minus 1 to just do the algebra, and this will become basically equal to 0. Okay, and then what? And then if we just solve for k, the roots will be something like this. K will be minus re plus and minus of square root of re squared minus 4 re minus 1, okay, divided by 2. And then if you just calculate the root, your k1 will just come out to be equal to 1 and your k2 will just come out to be equal to 1 minus re. Because you just take a plus sign here once and you just take the minus sign once here. So that's it. That's the roots of this of this equation for k. And of course, these are two linearly independent roots, which means that now my u theta bar as a function of r bar. So I considered it as some r power k, if you remember. That is something that I considered r power k. So this will just going to be r power k1 plus r bar power k2. So this means that my u theta is just going to be some constant a1 times r plus the other constant a2 times r bar power 1 minus re. So that's it. That's the solution for u theta. Okay. I'll stop here for some time. I hope the algebra and the logic and the way of how we solve the equidimensional equation is clear, basically. And now we'll see something very interesting. Okay, I hope this is clear. So let's now try to find out these constants a1 and a2. So for that, obviously we need to use the boundary conditions. So what are the boundary conditions then? So the boundary conditions, if you remember, was something like this. So I have u theta. So I had u theta at r equals to a, that was equal to omega a. And then I know that my u theta c, the characteristic scale, was just omega a, which means that my non-dimensional u theta bar at r bar equal to 1 this is just going to be equal to 1. So that's one of our boundary conditions. And the second boundary condition is that the disturbance, the velocity basically goes to 0 at far field, which means that u theta bar at r bar tending to infinity is basically equal to 0. Okay. Now let's use these boundary conditions in this. So I'll name this as some equation 5. So let's try to use the boundary conditions. Let's say this is 5a and 5b into 5. All right. So now what you can see is that, okay, so what we'll now do is 5a and 5b, we'll substitute this into 5. So you can now see a very interesting case here. So if you have a closed loop at equation 5, if my Reynolds number, okay, is less than 1, okay, try to understand what I'm trying to say. If my Reynolds number is less than 1, okay, because see, whenever my r bar, so this, first of all, this is r bar. So whenever my r bar goes to infinity, this term will always go to infinity. Okay, will always go to 0 because I have a 1 by r bar term here. So I don't need to worry about this term. But if my Reynolds number is less than 1, then when r bar basically goes to infinity, this term will essentially shoot up. But I know that when r bar is at infinity, my u theta is basically 0, which means the only way it is possible is that when my a2 is basically, so a2 has to be equals to 0. That's the first thing. So I hope you understand. So what I'm trying to say is that since I know that when r bar goes to infinity, my velocity is bounded, but I know that for Reynolds number less than 1, this term blows up, which means that the only way to control this term and to keep the velocity bounded and finite and the velocity in fact to be equal to 0, I must have a2 equal to 0. So what it means that I'll write down here, for Reynolds number less than 1, the boundedness condition gives us, it gives us that my a2 equals to 0. Okay, and then I have one, and then I have one more, and then I have one more condition, which is u theta at r equal to 1 is equal to 1, and from that I will get a1, meaning that for Reynolds number less than 1, it is possible for me to get closed form solution based on the boundary conditions that we have. So that's what I'm trying to say. So for Reynolds number less than 1, I know that my a2 is equal to 0. Then what I will do it, I'll just apply this u theta bar at r bar equal to 1 is equal to 1, which means I have what? Which means that my a1 is just going to be equal to 1. So therefore, my profile for u theta bar as a function of r bar is just going to be 1 by r bar. Okay, because you have uniquely determined the constants a1 and a2, and this is what the velocity field for u theta bar would be. Okay, but that is for Reynolds number less than 1. Okay, now let's look at the other way. For Reynolds number, so what will happen for Reynolds number greater than 1 basically? So greater than or equal to 1 to be precise. Okay, let's see the equal to 1 scenario. So when Reynolds number is equal to 1, this would be this term would basically be going to r bar power 0, which means 1, and then if this is 0, okay, so I think this is not for equal to 1. For equal to 1, I think you can still get a kind of unique solution. I will safely say this is for Reynolds number greater than 1. Okay, equal to 1 is the scenario that we'll investigate separately. So what I'm now trying to say is that when my Reynolds number is now greater than 1 strictly, then what will happen is that this term would basically be, so 1, so if my Reynolds number is greater than 1, then 1 minus Reynolds number, this will be less than, this would be what? This would be less than basically 0, which means now when r bar tends to infinity, this term will no longer blow up. I hope you can realize, which now means that I just have one condition to actually evaluate two constant a1 and a2, and this is not sufficient, right? Because one condition cannot give me two constant, because this constant will only say whether this term will blow up or not. And I said that for Reynolds number greater than 1, this term cannot dictate uniquely the value of A2 because of the fact that this term will now no longer blow up, and I cannot say that A2 will be equal to 0. So the bottom line is that for Reynolds number greater than 1, the boundary conditions are not sufficient to give me, unique solutions, is something that I want to say. So for Reynolds number greater than 1, the boundary conditions are not sufficient to give me unique solutions. And I hope you can realize why, the boundary conditions are not sufficient here. Okay. All right. So now at least we have a domain in which we can say, as I was telling you it in the beginning of the, exercise, that there will be a range of Reynolds number where, we can say that, okay, now we can get unique solutions. So for low Reynolds number flows, where Reynolds number is less than 1, that is for, for highly viscous flows, let's say, or for flows with, smaller dimensions of the cylinder, unique solutions are indeed possible, analytically at least. But for Reynolds number greater than 1, analytical solutions are not possible if we consider these boundary conditions. Okay. And for that, we need to solve this problem numerically, is something, that I want to portray here. All right, so let's then see this scenario. So let's now stick ahead into the Reynolds number less than 1 scenario, because Reynolds number greater than 1 will not give me unique solution here, at least for the boundary conditions that we considered in this scenario. So I'll write that we will now consider the Reynolds number less than 1. So if my Reynolds number less than 1, I exactly know that my U bar is just minus of 1 by R bar, UR bar is just minus of 1 by R bar, and U theta bar, as we just now calculated, is just 1 by R bar, basically, for Reynolds number less than 1. And my U theta bar is just going to be 1 by R bar. That's it. So we have obtained uniquely the form of the, the form of the velocity profiles in the limiting case when Reynolds number is less than 1, analytically, of course. All right. So the last step is that once this form is known, the only thing that we need to do now is to calculate pressure. So how do we calculate pressure? That's the thing that's the last step that we need to do. And we have still not used one more equation. And for that, and we'll use that equation to basically calculate what my P bar or what the pressure would be. And if you remember, that is nothing but equation 1, which is the R momentum equation. We'll just insert these velocities into the R momentum equation to basically get pressure. But remember, this is only possible when we are using these forms of the profile, and this is only possible when Reynolds number is less than 1, because of the physical nature of the boundary conditions that we have, and I explained why this is the case in this scenario. Okay, so what we'll now do is, considering Reynolds number is less than 1, we will insert the velocities in the R momentum equation. Okay, so the R momentum equation, if you remember, is this basically. It is just this. So we'll just use the fact that my UR bar is just minus 1 by R bar, and U theta is just 1 by R bar, to basically calculate what P bar would look like, basically. But for that, we need to evaluate certain things. We need to evaluate this term. We need to evaluate this term, and let's just do this. So what do we have? So if my UR bar is minus of 1 by R bar, then I know that my DUR bar by dr bar will just turn out to be 1 by R bar squared. And I also have this term, which is R bar times DUR bar by R bar, and this term would be just 1 upon R bar. And then this means that therefore the DDR bar of R bar times DUR bar by R bar, this would just be minus of 1 upon R bar squared. All this we are doing because we require this in the R momentum equation. Okay. All right. Then let's just insert this in the R momentum equation. So when we insert this, we'll get something like this. Okay. So we'll get 1 upon r bar cube, okay, minus u tilde squared. You can just do it at your end, it's just the math. uh, R bar cube, and then I have minus u tilde. Remember, u tilde is just a parameter which dictates the strength of the flows. And then I have minus del p bar by del r bar, and then I have terms like this, minus of 1 by, you know, r bar cube plus 1 by r bar cube times 1 by re. And these two terms will basically cancel each other, which means that for the pressure, I just have a simpler equation of these from 1 plus u tilde squared by r bar cube, and this is equal to u tilde by del, what this becomes, del p bar by del r bar. And since my pressure is also just a function of r, I can simply, write it as dp bar by dr bar times u tilde is equal to 1 plus of u tilde squared by r bar cube. And then I can just do a separation of variables here, where I can just write dp bar as this is just going to be 1 plus u tilde squared by u tilde, okay. And then I have just what, dr bar by r bar cube, and that's it. We'll just integrate it, and if we integrate it, what we'll get is p bar as a function of r bar, and this is just going to be 1 plus u tilde squared by u tilde times minus of 1 by 2 r bar squared. Okay, that's the integration of 1 by r cube. Basically, that's what we did. Okay, plus a constant, let's say c2. But we know that, so what do we know? So in order to calculate c2, we know that my pressure p when r tends to infinity is basically some p naught. Okay, and if I non-dimensionalize it, I can just say that my p bar when r bar tends to infinity is basically p naught by pc, and pc is nothing but rho omega squared a squared. Okay, and yeah, so this means that when r bar basically go to infinity, my pressure would basically be this. So if I just invoke this here, let's say so let's name this equation again. So this would be what? This is 5, then this would be 6. This is just 6. Okay, so if I just, so and let's name this as 6a. So if I just substitute 6a in 6, what I will get is that my c2 will basically be equal to p naught by rho times omega squared a squared. Okay, which is again a non-dimensional quantity because this has got the same dimension as p naught. Okay, and this means, so what does this mean? This means that I have now uniquely determined pressure in the limit, of course, when Reynolds number is less than 1, as p bar as a function of r bar is something like this. So it is just 1 plus u tilde squared by u tilde, okay, times minus of 1 by 2 r bar squared, okay, plus c2. C2 is just going to be p naught by rho times of omega squared a squared. So that's it. That's it, guys. We have uniquely determined the pressure, but this is only true for the limit when, Reynolds number is basically less than 1. Okay, that's the solution for pressure. For Reynolds number greater than 1, the boundary conditions that we just took are not sufficient to, give us unique solutions in this exercise. Okay, there is something which is known as, a stronger boundary condition in this scenario is that if you there is something called circulation. If you say that my circulation is basically constant, then you can get analytical solution up to Reynolds number equal to 2. But beyond 2, again, you will say that, okay, this condition will not show it here, but you can define something called circulation and then say that if your circulation is constant, you can get analytical solution up to Reynolds number equals to 2. That is Reynolds number less than 2, basically. But beyond Reynolds number greater than 2, the boundary conditions, even though if you take circulation as a boundary condition, is not sufficient to give you, analytical solution is the idea. But anyways, for Reynolds number less than 1, we have determined uniquely what is going to be my pressure, okay, what is going to be my velocity fields, and all the other pertinent things that we are asked. Okay, so that's it. So I hope you can now realize that you can always write your pressure as some disturbance pressure plus, the far field pressure, which is P naught basically. So you can also see that this is how the disturbance pressure look like. So this is actually the this term is actually the disturbance to the pressure field. Disturbance to the pressure field. Okay, that's it. So that's it, guys. We have uniquely, determined the velocities. I hope you like the problem, because this problem indeed gave us many insights. First, the power of non-dimensionalization, the strengths. Okay, because see, this term u tilde has so what is u tilde? It is omega a by u. So let's say if I have a case when there is just suction, meaning that u tilde is basically equal to 0. Okay, then what do we get? Then of course this is then this is just 1 by 0 times this. So this is, then this is the problem. Then we need to we need to change the scales as per the solutions here. But it just gives us a multitude of insights into what, sorry, this is not, yeah, okay, this is u tilde basically. Okay, okay, I think, yeah, I think this is fine. Okay. All right. Anyways, so the point is, please check the algebra at your end, because this is something that I did from my end. But the fact that we now get a strength, so we now get a solution which dictates how the strengths of the two mechanisms delineates delineates the variables like the pressure field, the velocity field, and things like that. Okay. Uh, this is something that I want to portray through this example. It's a 2D problem, but we simplified this to a problem where we essentially need to solve for both pressure and the two velocity fields, and the resulting solutions or ODEs basically uh, in this exercise. Okay, so that's it. This is where we will stop here today. I'll wait here for a couple of minutes. If you have any questions, you can ask, or if you have questions in the middle of the week also, you can always feel free to post it in the discussion forum of the course. And as you can see, we will be happy to take the questions in the discussion forum as well. So it is true that we are not solving problems exactly what is there in the assignment, because the problems that there in the assignments, is the straight away things that are asked if you just see the lecture series. But these problems will give you insights, and I hope you realize that, like, how do we non-dimensionalize things, and how do we basically go ahead and solve these kind of problems where we need to understand the scales of the various quantities of interest. Okay, so yeah, so that's the point. If you have any questions, you can ask. If not, we have solved this problem. Just to give you a recap, so we'll finish by just giving you a recap, because it was indeed a long problem. So what we did is, we were basically trying to solve for the fields, the velocity fields ur and u theta, and also the pressure, for a problem where there was a cylinder which was rotating in counterclockwise sense with some velocity omega, and there was a radial suction, maybe because of the fact that the cylinder surface is just porous. It has some pores on its surface basically, due to which that there was a inflow of fluid taking place to its surface with some radial suction velocity u. Okay, so based on this and considering the assumptions, we started off by writing off the characteristic scales. I mean, the characteristic scales were given, so we started off by writing the non-dimensional variables, plug the non-dimensional variables into the dimensional equations, for instance the r momentum equations, to get the non-dimensional r momentum equation, and similarly the theta momentum equation to get the non-dimensional theta momentum equation. And then we saw that these two equations were coupled, so it's like solution of one depends on the solution of the other. So we took the help of the continuity equation, and we saw that indeed by solving the continuity equation, we could get the r velocity field, which is just minus of 1 by r to be precise. And then we use this velocity field to get the u theta uh, u theta component of velocity field by solving something which is known as a equidimensional equation, or this is known as an Euler-Cauchy equation. And then we took the solution form of u theta as r bar to the power k to basically solve this Euler-Cauchy equation. And then we argued then under a certain range of Reynolds number, we can get we can get unique solutions, and beyond that Reynolds number, unique solutions are not possible. And the critical Reynolds number came to be equal to 1. Okay. And then we said that for Reynolds number equal to 1, we saw that u theta indeed came out uniquely to be 1 by r bar. And then under this, limit when Reynolds number is less than 1, we use the form of ur and u theta into the r momentum equation to get the solution for pressure, basically. And this is what pressure looks like, of course, in the limit when Reynolds number less than 1. And this is basically the target of this objective. So I hope you liked it, or you understood, and I hope you understood what we basically did here. So we'll stop the discussion here. If you have any questions, you can feel free to ask it in the discussion forum, or we will meet in the next week. Thank you very much. We'll see in the next week. We'll see each other in the next week. Thank you.